Welcome to Saveetha Dental College Lecturecast in Biostatistics. This is Dr. Deepak, and we shall look into Descriptive Statistics Part 2. So, the primary aim of this session is to cover about histograms, box plots, normal distribution, central limit theorem, and kurtosis. First, let's look into histogram. A histogram is a graphical way of representing the magnitude and frequency of data presented. For example, if you look at the couple of squares in front of you, you observe that the blue is the most common color, but it's very difficult for you to manually count and determine by how much blue is greater than red or purple. However, when you rearrange these squares into a nice little histogram, you get a clear idea as to how much each group is and how they differ from each other. Next, let's look into Boxplot. It's a very popular way for representing non-normal distribution of data. For example, if you look into the data set distributed from 3 to 35, you notice that most of the values are closer to 3 and fewer values are distributed closer to 35. And when you determine the median of this group, you find out that the 50th percentile lies at the value of 12. And if you further go down to determine the quartiles, which is basically half of the median, you determine that the 25th quartile is at 8 and the 75th quartile is at 27. So a box plot would actually be a bar between the first and the third quartile with a thick line indicating the median. So the distance between the median and the quartiles explain as to how uneven the distribution is. If the median lies exactly in the middle of the box, it means that the data is more evenly distributed. When you look at a box plot, sans the values, you would understand the median and the two quartiles forming the terminal ends, and a completed box plot would also have the minimal and maximal values. By this box plot, it's very obvious that the majority of the values are concentrated at the lower end of the median or lower end of the spectrum. The next topic is on normal distribution. Normal distribution has already been covered in part 1, however we have covered it with more vivid details here. So normal distribution is a data set which has even number of data points above and below the mean. For example, if you have 100 people and your mean is 50, so the number of people above 50 and the below 50 should be equal. A non-normal distribution would be such that majority of the data points lie above the mean, whereas it could also lie below the mean as shown in this graph. So the significance of non-normal distribution is that they do not follow the central limit theorem, which will be described soon. And since they do not follow the central limit theorem, the type of statistics required to analyze non-normal data is also quite different. One should always remember that non-normal data, once the sample size becomes much larger and larger, they have a tendency to come back to normal distribution. So the next topic for the discussion is the central limit theorem. It's a very interesting prospect of normal distribution. For example, if you have the mean, which is shown as x bar in this graph, and a normal distribution showing the number of subjects under various values, sigma 1 being the standard deviation and sigma 2 being two standard deviations from the mean. So according to the central limit theorem, 68% of all data values will usually be present within one standard deviation of the mean. 95% of all data values can be found within two standard deviations of the mean, and 99.6% of all values will fall within three standard deviations of the mean. This rule and the way the distribution happens is universal to nature. For example, whether the length of the hair or it's the size of the planet, they would follow these rules. For example, 68% of all the planets would have the diameter similar to one standard deviation from the average diameter of planets, and the same thing would be applicable to anything in nature. And the benefit of this information is that you can determine the percentage of data above a particular cutoff point. For example, in this problem, if someone were to give you the mean of a group is 100 and the standard deviation is 15, find out the number of people or percentage of people above 130. So the answer would be The data between 85 and 90, 115, that's one standard deviation, is 68%. The data between 70 and 130 is 95%, which is two standard deviations. Data below 70 and above 130 will be 5%, which is basically outside of 95. And data above 130 would basically be 5 divided by 2 because it's evenly distributed on either sides and you get 2.5%. Hence, 2.5% of the data or 2.5% of the population would have a score greater than 130. So this is a very useful tool, and that is why normal distribution has so much importance in statistics, and we try or strive to get most of our data into normal distribution. Many statistics are available to determine if the present data in the population or within the sample has a normal distribution or not. So the last but not the least is kurtosis. Kurtosis speaks about the steepness of the bell curve. If the bell curve is very steep, it means that the standard deviations are closer and most of the data is around the mean and there is very little variation between the group. This means the group is more homogeneous. Similarly, if the bell curve is much shallower and it's not very steep, you notice that the standard deviations move away from the mean and that the group is much more heterogeneous, and so the data or any findings of the study may be subjected to the variability within the subjects. Okay, and with that we would finish descriptive statistics. Thank you, and I hope you have a nice day.